Right, we will see here one more image parameter after image impedance, that is iterative impedance. So here, as per the definition of iterative impedance, if the impedance seen from port 1 is same as the impedance with which the other port is terminated, it means it is about port 2 only, right? So anyways, it is no need to specify here because they are equal. What it is saying, if the impedance seen from a port is same as the impedance with which the other port is terminated, then that particular impedance is known as iterative impedance. And make a note here, this is not about any particular type of network, that is symmetric or unsymmetric. This is about a network. So make a note here, it is not like it is for not for symmetric. You will understand why I am specifying here it is not for symmetric. It is for a generalized network, because you can see here it is Z1, Z2 and Z3. So if the impedance that is terminated and the impedance with which the other port is seen are equal, that is one value, then we can call them as, we can call that as iterative impedance. And also it is not like we will terminate only one side and the one side is only seen always. So we will be reversing the thing like image impedance. That means if this is ZT1, we will have another case where ZT2 is terminated here and the impedance with which it is seen this side is ZT2. So that is possible in both ways, right? So but we will see this for ZT1 case. So how to derive ZT1 here? So ZT1 is nothing but Z1 plus Z3, Z1 plus parallel combination of Z3 and Z2 plus ZT1, right? You can see that here, fine, because here Z1 and Z2 are in series and that combination is in parallel with Z3. The total combination is in series with Z1, that is only given here. So if you solve this or if you simplify this equation, you will get one algebraic equation. And one more thing here, we are assuming that Z square is Z1 Z2 plus Z2 Z3 plus Z3 Z1. Just to avoid this complex equation, we have considered this entire term as Z square, so which is only written there, fine, right? So with this quadratic equation, we will get ZT1 using minus b plus or minus square root of b square minus 4ac by 2a formula, that is the solution or the roots of quadratic equation. And we will be neglecting the minus case because we know that minus impedance doesn't exist here, right? With that particular case, we will consider only one thing, right? That is for ZT1. So similar to this ZT1, we can even get ZT2, right? So we can, without derivation, we directly kept it here because you can proceed for obtaining ZT2 in the same manner, where port 2 will be port 1 will be terminated and port 2 will be seen with the same impedance, and they are called as ZT2 now. Okay, right? So now in these formulas, so what is this Z square here? Don't worry about Z square. Z square is nothing but it is considered as Z1 Z2 plus Z2 Z3 plus Z3 Z1, right? So now we got iterative impedances which are known as ZT1 and ZT2. So this is not for a symmetric case, right? Because Z2, Z1 and Z3 are different. So for symmetric case, what we can consider the condition of Z1 is equal to Z2. So when you substitute Z1 is equal to Z2, what do you get here? You will get Z, and that too equal, which is equal for ZT1 as well as ZT2. So both becomes equal to Z, and when Z square is this one, so Z will be under root value, right? Fine. So this thing you can get for a symmetrical network. That means we got already image impedances which are equal for a symmetrical network, and now we got the iterative impedances are also equal for symmetrical network. And if you observe, the image impedance for symmetrical network Z1 square plus 2 Z1 Z3 under root is equal to the ZT1 ZT2. That is very important here. So that means for a symmetrical network, all image impedances as well as iterative impedances are becoming equal. So this formula is very important. For a symmetrical network, it can be asked in numerical bits. Fine. So this is about iterative impedance. Next we will be discussing the most important parameter, that is characteristic impedance, in the next lecture. Thank you.